So let's meet our second strong oxidizer. So once again, this is considered to be a strong oxidizer, and so for primary alcohols, that will take it all the way to the carboxylic acid. Now, in this case, I'm showing it in the context of a secondary alcohol, although it's the same mechanism as what we'd expect for a primary alcohol. So this is the chromic acid reagent. And so effectively, it's this chromic acid in the presence of sulfuric acid and H2O. Okay, so that's normally how the reagents are shown. So this is definitely done in an environment, an aqueous environment, that is an environment in the presence of water. So the first step, in a sense, is to prime the chromic acid to make it, in a sense, more electrophilic. And so there are various ways of showing this. I think because we know that this is done in aqueous acid, it'd be a good idea to start off with the hydronium ion. So I'm going to skip a step here in the sense that I'm already going to start with a protonated OH group right here. And effectively what happens, of course, this would be protonated in the presence of our aqueous acid. Effectively what happens is this then gets lost and we form this better electrophile. Correspondingly, we have the attack of the alcohol with this good electrophile. So the attack would happen something like this. And now we have a good leaving group on our alcohol. Once again, there's a deprotonation step. If you think of the fact that this is done in an aqueous solution, then the best base to remove that proton would indeed be water. So the proton gets removed, and now we really do have a leaving group ready to leave with an elimination reaction. Now again, we need a base, and of course the best base available will be our water molecule. Now this will seem a little unusual in that our water molecule is actually being involved in what looks like an E2 reaction, but the idea here is that we have such a great leaving group that effectively we believe that this happens all in one concerted step. So the pulling off of that proton, the forming of a pi bond, and the leaving of the leaving group. And now we have the formation of this ketone. So we've looked at two reactions involving two strong oxidizers. The first one taking a primary alcohol to an aldehyde, the second one taking a secondary alcohol to a ketone. So now let's look at what happens with these strong oxidizers once we have these intermediates that form. And I'm using the example here of our primary alcohol and the corresponding chromic acid reagent. But as mentioned, it would also be true if we were doing this with bromine in the presence of the sodium hydrogen carbonate. So the first step, of course, is the oxidation of our alcohol to the corresponding aldehyde. Now, because this is done in an aqueous environment, there's something else that happens once the aldehyde forms. And that is, we form this hydrate. We'll examine the mechanism that's involved in forming this hydrate. But for now, I just want to take a bird's eye view. This is crucial in order to have further oxidation. So while this might seem kind of a trivial point, like it's okay, you've got this water, big deal. Well, the fact that you've got this water means that ultimately the hydrate can form. The hydrate has these OH groups, and these OH groups are susceptible for further oxidation. Now, again, because this is the aldehyde, it has this removable hydrogen, and therefore the aldehyde can be oxidized further. If we were to consider a similar situation of a secondary alcohol, and using the same reagents, so the H2CrO4 in the presence of H2O, H2SO4, and of course, the secondary alcohol, having one removable hydrogen, will form the corresponding ketone. Now, even if this is an aqueous environment and we can form the hydrate, so I'm just showing you here the hydrate. It's not going to look like a very good tetrahedral. All right, so there's my hydrate. You'll see that the hydrate that forms from a ketone has no removable hydrogens. So because there are no removable hydrogens, the ketone cannot be oxidized any further. Although the ketone may react with water to form this hydrate, there's no further oxidation. So the furthest we can oxidize a secondary alcohol is to the ketone. The furthest that we can oxidize a primary alcohol in organic chemistry terms will be the carboxylic acid. So to finish this video, what I'd like us to look at is what's the mechanism involved in forming the hydrate? And then once the hydrate is formed, well then what's the subsequent oxidation step? So here's the mechanism for the formation of the hydrate from an aldehyde. Now we could also show this mechanism for the formation of a hydrate with a ketone, but as we just saw, that's not really that useful because that particular hydrate cannot be oxidized any further. I will say that this mechanism will be reviewed again when we look at the reactions of ketones and aldehydes with various nucleophiles. But we need to see this right now, so we're going over it. Now, in this particular case, because water is a poor nucleophile, essentially, what we need to do is make the carbon here, the carbonyl carbon, very attractive to that water molecule. And so this is done in the presence of acid. And so effectively what's going to happen is we're going to protonate the oxygen of the aldehyde. Now the oxygen of the aldehyde is not particularly basic. And so the equilibrium is actually going to lie in favor of the aldehyde. But all we need is a small portion of the hydrates to form, and then their subsequent reaction, that then the equilibrium in a sense will be driven forward as more and more product will form. So given that we have some aqueous acid, we might imagine that we can use a hydronium ion as the source of a proton. The oxygen picks up a proton, and what we correspondingly have now is this protonated aldehyde. That is what gets attacked by our water. So the water in this context is going to act as a nucleophile. So it will attack at our carbonyl carbon. So it will form, in a sense, another alcohol group, and we have a protonated alcohol group, and we still have a hydrogen. Now we have water not acting as a nucleophile, but rather acting as a base, picking up that proton. And as such, we'll now have our hydrate. And this is a hydrate with an available hydrogen, or a removable hydrogen. And so once again, that will allow for further oxidation. As a last step, let's just look at what now happens with this hydrate with the removable hydrogen in terms of the oxidation with chromic acid. The same process can also be described using the bromine and the hydrogen carbonate. So to facilitate this, I've provided a scaffold in your course pack that you can fill out to watch for this mechanism. So here we have our good electrophile. And so we'll start off with our hydrate attacking the good electrophile, forming an intermediate that involves a protonated oxygen. We'll have the deprotonation step, where water will be acting as our base, so picking up that proton. Now we have a leaving group all primed, and here is our removable hydrogen. And once again, we'll have water act as our base here. So water will pick up that proton. Pi bond will now form, and we'll lose our leaving group. And you can see that instead of now having what corresponds to an aldehyde, we've oxidized further to a carboxylic acid. And so this is an additional oxidation step. To be clear, this cannot happen unless we've got water to form the hydrate and unless we have a removable hydrogen. Now, one of the things that you might be wondering is, if we have a primary alcohol, and what if we only want to oxidize to the aldehyde? We don't want to oxidize all the way to the carboxylic acid. Can this be done? And indeed it can, and this will be the topic of our synchronous classes. We'll also do some review so that we sort out all the different kinds of oxidations that can happen, and so that you can practice predicting the kind of products you're going to expect to have.